I will start sharing my screen and I'll move around a little bit to get set up. And there we go. I will present during the next, let's say, half hour, the instruments, 5 instruments we used at Cfht. I will mention some opportunities and services. If there's something that I don't talk about, if you have a question, we'll have time at the end. You can always email me. And if I don't have the answer today, I will find somebody who has the answer. Cfht is a facility which is located near the summit of Mauna Kea at an elevation of 4,200 meters. It's on the big island of Hawaii. The facility is a little over 40 years old, but we are still very productive. This is an image of the inside, and you see, I think, 3 staff members to give you a sense of scale. And this is a recent picture of part of our staff. We have like 40 or 40 staff members. This picture was taken last fall when we redid the aluminization of our primary mirror. Cfht and the staff, we acknowledge and recognize that Mauna Kea, where we work, is a historically and culturally very significant site. Therefore, we perform our daytime operations and nighttime observations with care and respect. You might wonder, what can you do with a 6 telescope like Cfht? Well, this is actually a trick question because it depends what kind of instruments are installed on the telescope. All right, so what has Cfht observed with its suite of 5 instruments? Not sure where to start. Well, I could start with Sirius. And yes, I am serious. We have observed the brightest star in the sky with our 3.6 meter telescope. Of course, in order to protect the detector, we have dispersed the light of that very bright star over the whole detector. We did high dispersion spectroscopy, high spectral resolution spectroscopy, using an instrument that is called Espadons. For Sirius, took 1 second exposures, and that allowed the principal investigator, the PI, to get spectra with a signal-to-noise ratio between 500 and 1,000 per spectral resolution element. And you see here just a small subset of one such spectrum. Espadons, you can observe stars that are as faint as magnitude 16V. You can reach a signal to noise of about 10 in about an hour. It depends on the conditions. You can integrate longer to get better signal to noise. You could also integrate longer to faint stars. However, the limitation.
Oh no.
Look, okay, it looks like we lost her for a moment there. I'm sure she'll be back. As she mentioned, the bandwidth in Hawaii is not optimal, especially on the Big Island.
All right, I'm back.
Perfect.
Let's do this. All right, I'll share my screen again. So that's where I was. Let me rearrange my windows a little bit. Hopefully I won't lose the connection again. So the limitation at Cfht is that for Espadons, the acquisition camera.
Oh, Nadine, I don't think you are sharing your screen with us.
It says share. Oh. So let me stop and try again. I'm stopping. I'm sharing again. So you should be looking at the slide with Espadons and the spectra.
Unfortunately, I'm still not seeing anything, and I just got a message from another member saying that they aren't seeing anything either. Would you like to quickly send me your PowerPoint? And then, here we go.
Yeah, I think it just might be an issue with just lagging. So I'll have to be careful to go not too fast. so I don't lose the connection and so that the slide here.
Okay, and if you feel more comfortable, feel free to just send me your slides if you want instead, and I can go and I can click next. But until then, we'll try this.
Yes, and I will also provide you with a PDF file of those slides so people have something to refer to later on.
Wonderful, thank you.
So with espedons, we don't really go fainter than 216 because it's really hard to do. So you might wonder about going fainter than magnitude 16 in the optical. Well, the trick would be to not disperse the light as much on the detector. So instead of doing spectroscopy, you should do imaging, do optical imager, which is something that we do have at Cfht. Our optical imager is called Megacam, and I'll provide the detailed specifications right after this. On Megacam, you can put a star which is as bright as magnitude 6 or 7. However, these bright stars will create halos and contaminate big chunks of the mosaic. So it's possible, but you lose some of the field. However, because you have an imager, you can reach a signal to noise ratio of about 10 in 20 minutes and go as deep as G magnitude 25 magnitude or something a little bit fainter than that. And of course, it depends on the conditions in the sky. With an imager, you don't have much spectral resolution. However, you have spatial resolution. You have a big field of view. This is a raw image of Megacam, which has CCDs. And as you can see, you can observe extended objects with an optical imager. If you take images in different filters, if you do a dithering pattern to fill in the gaps between all the detectors, you can produce pretty images like this one produced by Hawaiian Starlight. Beautiful color picture. So that's in the optical. How about going into the infrared? Infrared, yes, we can do that. We can near infrared spectroscopy and imaging. Spectroscopy, we have a near infrared spectrograph, spectropolarimeter, and also velocimeter called SPIRU. For technical reasons, the shortest exposure time is about 30 seconds, and we can reach a signal to noise of around 300 for a star of magnitude 3 in H. And this is just a small chunk of a SPIRU spectrum for such a star magnitude 3 around a signal to noise of about 300. With that spectrograph, we can observe stars as faint as magnitude 15 in H, and we can reach a signal to noise ratio of about 5 in an hour. That gives you a sense of what you can do. We also have a imager. And in this case, you can reach a magnitude a little bit fainter than 23 in H, and again, reach a signal to noise of 5 in an hour. And this is an image taken by the WIRCam imager, a nebula that you probably recognize, even though the image is in the infrared. You might want to do imaging and spectroscopy at the same time. Well, you will be happy to hear that, yes, we can do that because we do have an optical imaging Fourier transform spectrometer called CTEL. With such an instrument, you take a series of images, a cube of images. On each image, you have the image, the extended object you are observing, but each image actually has fringes because the instrument is an interferometer. So the cube of raw images is a set of images with fringes. And by using the proper data reduction software, you can transform that to a cube of images where each image is at a specific wavelength. This means that you could take one image anywhere in the cube and that will show you a specific wavelength, and you can see the morphology of the object at that wavelength. Or you can take 1 pixel in that image and go through and get the whole spectrum at that location in a nebula or a nearby galaxy. That is a very powerful instrument. This is an image from a very recent press release, and I give you the URL here. It's an nebula. In this case, what the astronomers have been able to do is to map the filaments and the gas clouds in the nebula to make a 3D map of the object. The reason why you go out this URL, it has a video where you actually go in and out of the nebula and see it rotating. It looks from outside to inside. It's really impressive. This plot shows you the atmospheric transmission on Mauna Kea. So we are at over 4,000 meter elevation. You have the wavelength at the bottom from the far UV to the near infrared, about 3 microns. And at the top, you have 100% transmission. You see that Megacam in blue, Espadons in green, CTEL in yellow, cover the optical range of the spectrum. WIRCam and SPIRU are in the near infrared, and there's a slight overlap between Megacam Espadons and WIRCam and SPIRU. I'll give you now more detailed specifications for each of the instruments. Let's start with both spectropolarimeters, Espadons and SPIRU. Espadons in the optical, SPIRU in the near infrared. With both instruments, you can do simple, straight spectroscopy. For Espadons, you can either get the spectrum of just the star, or if you're interested on the same exposure, you can get the spectrum of the star and the sky at the same time. For SPIRU, there's only one spectroscopic mode. You can only get the spectrum of the star. If for some reason you need the spectrum of the sky, you have to take a separate exposure. Both instruments are polarimeters, and we can do linear or circular polarization. The polarization in the continuum is subtracted by the data reduction pipelines, which means that those instruments are optimized to measure or to see the polarization in lines, emission or absorptions with respect to the continuum. You have the wavelength coverage of Espadons and SPIRU with the slight overlap between the two instruments. The spectral resolution is quite similar, around 70,000. And of course, the resolution varies across the spectral order, so it's not exactly the same for all wavelengths. With Espadons, if you just use the comparison lamps, you can reach a radial velocity precision of between 100 and 200 meters per second. And again, this depends on the wavelength and the spectral order. However, the data reduction pipeline takes advantage of the fact that there are telluric lines in the spectra, and that allows us to improve the precision to about 20 meters per second. SPIRU, which is our newest instrument, is also a velocimeter. It can do radial velocity at a precision. Our goal is to do 1 meter per second. Right now, we are at 1.5 to 2 meters per second. So there's a big difference between the two instruments. SPIRU is ideal to look for, detect, or study exoplanets because of that radial velocity precision. Our two imagers, Megacam and WIRCam. Megacam has 40 CCDs that cover about 1 square degree. WIRCam is a little bit smaller. The field of view is about 22 arc minutes by 22 arc minutes. Both instruments are cooled. In the optical, we cool because a cool temperature improves the quantum efficiency of the detector. Whereas in the infrared, we have to cool even further because we're fighting the thermal background, which contaminates and brings up noise in the images. Megacam, we have 11 filters available. There's only 8 that we can put in the instrument at a time. For WIRCam, we have 13 filters and only 8 at any time in the instrument. For Megacam, it's relatively easy to switch one filter for another. We can do that during the day, However, for WearCam, the filters are cooled. So if we absolutely need to change filter, we have to warm up the instrument, swap filters, pump, and then cool again, which is a operation, and it's also a little bit risky for the detectors themselves. I'm also providing you the wavelength coverage and the fact that a pixel on Megacam is about 0.187 arc seconds, whereas the pixels on WearCam are a little bit bigger, 0.3 arc seconds. These graphs show the Megacam filters. We have 5 broadband filters, U, G, R, I, and Z. And you'll notice that the U filter really goes far in the UV. We are taking advantage of the fact that we are on Mauna Kea. There's more transmission in the UV. So we have a filter that takes advantage of that. We also have narrowband filters, and we have a very broad GRI filter, almost white light. It just lets in a lot of light from different wavelengths. For WearCam, I don't have plots. However, I have a table that shows first the broadband filters covering Y, J, H, and K, and then the suite of narrowband filters that we have at different wavelengths for different purposes. CTEL, the Fourier transform spectrograph, has a field of view of about 11 arc minutes by 11 arc minutes, and each pixel is about 0.3 arc seconds. The wavelength coverage is a little bit narrower than for Megacam or Espadons, from 350 to 930 nanometers, and we don't cover all of that in one chunk. Depending on the filter that you are using, you will cover a subset of that range. The spectral resolution, you can customize that. You can select that, and it can be between 1, which is basically an image, up to 20,000. The filters for CTEL are the following. So you see the wavelength range for each filter from the blue to the red. All right, how about science projects and discoveries? What can you do with those 5 instruments? The reference I'm giving you here is a link to our press releases and news item, where you can find for many years, years past, different discoveries that we have made using all of our instruments. Also, on the following page that is indicated here, which is the QSO page, at the bottom, there's an archive where all the titles of all accepted programs are listed. For all semesters and all instruments, if you want to get an idea or a sense of the type of science that you can do with an instrument, you can first start and take a look at that. At Cfht, we have observed a little bit of everything. We have done asteroids, either to discover them, to confirm their existence, to characterize their orbit. We have done comets, other types of minor bodies in the solar system. We have also observed planets and moons in our solar system, like Venus, Mercury, and the moons of Jupiter. We observe stars of all kinds, dwarfs, giants, supergiants, very red dwarfs. We have done brown dwarfs. We also do nebulae and disks around stars, exoplanets. We study the interstellar medium, gamma ray bursts, stellar magnetic fields, stellar black holes. We study strings of stars, especially around our own Milky Way, but also tidal tails around other galaxies. We can do studies for star clusters, for nearby galaxies, galaxy clusters, galaxy halos, black holes at the center of galaxies, QSOs, quasar, and then there are also programs that look for gravitational lenses, dark matter, or studies of cosmology. So we cover really a little bit of everything. We do as much as we can, given that we have a 3.6 meter telescope. Megacam, we do from very nearby objects, a lot of solar system studies, up to cosmology. At Cfht, a few years ago, we started to get big programs. The first one was the Cfht Legacy Survey that was conducted between 2003 and 2009. And a very quick summary of that large legacy survey is that over 500 type 1a supernovae were discovered, and you see an image at the bottom. 10 million galaxies were imaged. The data was used to produce a dark matter map. Over 1,000 candidate galaxy clusters were identified, as well as 1,600 merging systems. There's a lot of data that has been obtained, and there are still scientific publications that are coming out because people are just using the archive. The data are public, and you can make a bunch of build new projects and make new discoveries. I cannot mention Megacam without mentioning Oumuamua, which was a visitor from our panel at left shows the discovery image. So you see a circle with a very faint trail at the center. That's an image that was taken by Pan-STARRS, which is a telescope on Haleakala on the island of Maui, just next door. And at Cfht, what we did and what we often do for Pan-STARRS discoveries is to confirm the existence of this object. And this is the image presented in panel B. And in that case, the object is the dot of light and the trails correspond to star trails. Cfht and also a lot of the other Mauna Kea observatories collaborated to gather additional data, photometry in different filters over time. And this has led a few months later to modeling of this object, which we think is shaped like a cylinder or a needle, although some think that a pancake-shaped object would also fit the data we have obtained. The panel at right, of course, shows you an artist's concept. Other solar system objects that have been observed at CFHT are Manx comets, which are like the Manx cat, objects that do not have a tail, comets without a tail. I give you the URL if you are interested in getting more information about these types of objects. If I move to WIRCam, since it observes in the infrared, we look for cool objects like dwarf stars, cool stars, brown dwarfs, free-floating planets, exoplanets, or dusty objects. At right, you can see the light curve of a transiting exoplanet from the raw data at top to binning the data, correcting it until you see the effect of an exoplanet as it transits in front of its parent star. With WIRCam, we have been able to do direct imaging of an exoplanet 155 light years away. You see on the image at right, the star itself, GU Pisces A, and then about 40 arc seconds further away, the very red but faint point of light, that's a direct image of the exoplanet around this star. There's also a very interesting project that was doing astrometry, but very high precision astrometry. The plot to the left shows in the purple square the size of a WIRCam pixel. So that box is 0.3 arc seconds on the side. Little blue dots show where this specific object has been detected. So you can see that by making careful observations, controlling the sky conditions, when we observe, how often we observe, this PI was able to basically measure the position of this object, the precision of 4 milli-arc-second, which is absolutely remarkable. And again, I give you the URL so you can see the scientific significance of this discovery. Moving on to Espadons. Espadons can do just straight spectroscopy projects. Its strength, since it is a spectropolarimeter, is to detect or characterize stellar magnetic fields. It can also do solar system studies. There are many stars with Espadons that have been followed nightly or every so often over many days or weeks. And when we do that, we see that the shape of the absorption lines change over time. And if we look at the polarization of those lines, that also changes over time. Those observations can be flipped over to reconstruct the magnetic field. Is it a simple dipole, or is it something more complicated with many loops? And we can actually detect, see if there is a magnetic field, and then characterize its strength. Many stars have been observed with espadons with that goal in mind. With espadons, we also had large programs. The first two were conducted between 2000 and 2012. The first one, called MIMES, Magnetism in Massive Stars, was a survey of over 500 massive OB stars. And two of the main results is that they found magnetic wind confinement in magnetic O stars. So those stars have a magnetic field, they also have a wind, and the magnetic field is confining, restricting where the wind is flowing. Another interesting result is that the classical BE stars that were observed as part of this survey, no magnetic field was found in none of them. The second large program on espadons targeted stars that are much smaller, less massive, protostars, and also their planets. And that program, instead of doing a survey, was doing a monitoring of about 30 stars. And two of the main results is that the magnetic field in those protostars is not fossil. It is not the magnetic field that was there in the interstellar cloud. It's not the magnetic field that followed all the particles as the cloud was collapsing to form the star. The magnetic field observed is actually created by the dynamo effect. So when convection turns on in those stars with the material bubbling up to the surface and then sinking back down, that creates a magnetic field. And the magnetic fields, when they are present, can also slow down a young star which is rotating. So we know that stars, when they form, they initially rotate quite fast. And if there's a magnetic field, that will slow down that rotation. I mentioned that espadons was used for solar system studies. One example is that we have observed Mercury. This is a restricted wavelength range of a full espadons spectrum. The wavelength range goes from about 5,886 angstroms to 5,896. This is where the sodium doublet is. The red line is a model or a reference spectrum, and in black you have the observations taken on when we were looking at Mercury, and you do see two emission lines. These two lines point to the fact that Mercury has an exosphere. It is not, are particles above the surface, and you can see that in that wavelength range. CTEL is an instrument that we started to use in 2015. So the discoveries are kind of just starting to pop up. One of the strengths of CTEL is that you can do maps of either the composition of a nebula or galaxy, or a map of radial velocities. And if you have a map of radial velocities, that can give you insight into the dynamics of the object you're looking at. This is NGC 1275, which has a black hole at the center. So there's matter falling into the black hole, but there's also matter which is being pushed out. By having this radial velocity map, the PI has been able to see that the motion in that area is actually chaotic. It's not ordered. It's not, very well constrained with filaments and flows. It is rather chaotic, which is a very interesting result. And I once again give you the link if you are interested in learning more about that. Spiru is an instrument that we started to use in 2019, but once again, discoveries are starting to appear. This is a very recent press release about an exoplanet that was observed around Eumic. Eumic is a very young star, 22 million years old. And the exoplanet is in orbit very close to that star. the period is less than 9 days. Here, with test observations, since it's a transiting exoplanet, the astronomers were able to get the radius of the exoplanet, and with the SPIRO observations, by measuring very precisely the radial velocity variations, we were able to get the mass. If you have the radius and the mass, you can get the density. And the result is that that exoplanet is just slightly denser than the density of water. How about getting you some data? Well, maybe you have an object in mind or a type of object in mind and you're not sure if Cfht is a good fit. You can start with our exposure time calculators. We'll find one calculator for each instrument on this web page, and the interface is different depending on the instrument you want to use. We highly recommend that you read the manual so you understand the units, the definitions, and the calculations for each instrument. But that can give you an idea. Do I need 10 hours of observing, which is a little bit too much, or is this something that I can wrap up in an hour or two? If you think you have an object or a set of objects and good idea, phase 1 right now is open for semester 2021B. The deadline is March 18. It's coming out shortly, but you might have time to submit a proposal, and I invite you to do that. If you have any questions about that, you can email us at phase1@cfht.hawaii.edu. If your program is accepted, like all our programs, it's going to be conducted under the queued service observing mode, and you can reach the whole team if you have a question by emailing us at qsot@cfht.hawaii.edu. The queued mode has this is the gist of it. There's no need to travel because we do everything for you. And especially right now, because of the pandemic, people can travel to start with. So this works absolutely great. We also do the best science first because we know what are the priorities of the programs. We know which programs are more scientifically important. So we will start with those first. We take the best calibrations because we know our instruments really well. We know how to calibrate them. We do efficient observations because we have trained observers who do that every night. And we do the observations exactly the way you want them to be executed. The proper configuration, but also the proper timing if the timing is critical for your program. Observation, we do the data reduction for you, for all the instruments. We provide you with the raw data, but more importantly, reduce data. What we mean by this is that we remove the instrumental signature. So we take biases and darks to remove the imprint of the detector on the data. We take flats. For the spectrographs, we do the wavelength calibration. If you take polarization data, we will do the polarization calculation for you. For the imagers, we do the photometry, the astrometry, and of course for CTEL, we do the Fourier transform for you. What we don't do is that the images or the spectra, if you have more than one for your object, we don't co-add that. However, there are tools at CADC where you can stack images, or you can look and see if some previously taken images have been stacked already for Megacam using the Megapipe tool, and also for WIRCam using the WireWolf tool. Generally speaking, the reduced data are available about a couple of weeks after the end of a run, so you don't have to wait for months. If you're not ready to write proposals, that's fine. You can still take a look at the data we have taken and look into the archives at the Canadian Astronomical Data Center that you can use in French or English. We have information regarding the past surveys and large programs that we've done. There's like over a dozen of them. And also about information about the 4 ongoing large programs. So this is the URL. And if on each of the programs, if you look towards the bottom of the page, you will find a link that should send you to CADC so you can get all the list of exposures and data taken for that specific large program. Here is a brief references for the Megacam surveys and large programs we have performed. Currently, we are still observing Vestige and the other large programs, CFIS. Those Vestige and CFIS are almost done. For Espedons, we had 5 large programs, and you can see their descriptions on those wedges. For Espedons, there's also an independent database of reduced spectra taken not only with Espedons, but also with its little brother, Narval, which is a copy of Espedons located at the Telescope Bernard Liot in France. This tool has very powerful query parameters. You can look for Cepheids, you can look for BE stars, you can make a query to get specific spectral types or distances, or pick objects whether they had a magnetic field detected or not. The output, the reduced data are presented as text files, and you also have spectra as plots, so you can see what the data look like. On WIRCam, we have had 3 from quasars to transiting exoplanets, and also a parallax program. The 2 ongoing large programs that just started a few semesters ago, there's one on Spirou Legacy Survey, looking for or characterizing exoplanets for the most part. And there's also a large programs on CITEL called Star Formation, Ionized Gas, and Nebular Abundances Legacy Survey. Here are other resources. If you're interested in Cfht in general, I invite you to look at our annual reports. The QSO webpage has the schedule, news items, links to the instruments pages, various tutorials. I once again give you the link for the call for proposal for 21B. You can email us, you can email me, we will provide you with an answer. And I will finish with this slide. The day that you finally get your first publication based on Cfht observations, we would like you to put the following acknowledgement, which is provided to you when we send you reduced data. It acknowledges the agencies which are involved with the operation of Cfht, and it also recognizes that the observations are taken from Mauna Kea, which is a significant cultural and historic site. I thank you, and I can take questions anytime now.
Thank you very much for that, Nadine. It was very illuminating, quite interesting. So if anybody has any questions, please feel free to go ahead and raise your hand, and I'll pick you out, or you can just open your mic. Oh, okay, I already see a couple. Caroline, would you like to start?
I don't have a question. That was just a clap for.
Ah, well, maybe I should learn how to read these emojis a little better. Okay. Actually, you know, if you have any questions, you really don't need to raise your hand. You can just open up your mic for right now. I actually have a question for Nadine while we wait. So Nadine, you mentioned the 14 different large programs that are going on at Cfht. When is the next call for large programs going to happen? Or do you know? Or is there going to be another call?
I think there's going to be another call for large programs. I've heard about it, but our scientific advisory committee is still thinking about it. So probably it's going to happen, but we don't have any of the details right now.
Okay. Are there any other questions?
You can also put questions in the chat if you want.
Yes, if you would prefer not to talk, that would be fantastic.
I had a question. I was wondering, you mentioned that you kind of do the best science first, like you prioritize your observations. I was just wondering, what's the process that you usually go about deciding which ones should be prioritized?
When proposals are submitted, they are given to a time allocation committee. So all the proposals submitted by Canadian PIs go to a Canadian time allocation committee, and their job is to rank the proposals. They give us a list, and at the top of the list, we see the most scientifically important programs. So the job is done for us because we have the ranks, we have the priorities, and we just code that with letters and numbers in our system so we can keep track of that.
Thank you.
So I see a question in the chat. What do we have to do to work at CFHT? Well, it depends what you're interested in. I assume that if you are interested in joining the astronomy group, we hire resident astronomers who have a PhD or are about to finish their PhD. That has happened more than once. We are usually looking for people who have observing experience, even with a small telescope, something on your campus, or 1.6 meter like Observatoire du Mont Mégantic. Sometimes we also look for people who have experience doing data reduction or dealing with catalogs of a lot of objects, coding experience to write pipelines. Those are the main skills that we look for a resident astronomer.
Okay, perfect. I'm not seeing any other questions at this point. So I would like to say thank you very much again, Nadine, for that wonderful presentation. Thank you. Oh, yes, Viraja.
I actually have a quick question.
Please.
So I was wondering how much percent of the time does the resident astronomer have for research, or like 100% of the time is dedicated to observatory work?
Resident astronomers have maybe a quarter or a third of their time available for science. So that's writing proposals, going somewhere to perform the observations, going to conferences, writing paper, reviewing paper, etc. And the rest of the time is CFHT duties, preparing the observations for a night, participating to testing a new instrument, monitoring the health of instruments, doing outreach, and other duties.
Okay, thank you.
I see there's another question in the chat. Actually, there are two. So the first one by Deborah Lockhorst asks, well, it says, first, thank you for the talk, Nadine. I was wondering what kind of surface brightness / faintness limits can be reached with CaTS?
I don't know the answer to that one. So if you send me an email, and I will be able to put you in touch with our instrument scientist, and we'll provide you with an answer.
If I may, it's something like 1 e to the negative 17 ergs per second per centimeter squared per arc second, something like that. It's quite impressive.
Yeah, there's no way I would have known that answer.
Sorry, I work with CaTS, and that number always comes to my mind.
Sorry, what was that, Carter? Can you repeat that?
Yeah, it's something like 1 e to the negative 17 ergs per second per centimeter squared per arc second.
Okay, great. Thanks so much.
It's so very impressive. It can get pretty low.
Yeah. Thanks, Nadine.
All right, so we have another question from Jean Malone. Is there a quota for proposals that are not part of a long-range mega project? One gets the idea that this may be quite small.
Yes, indeed. When we have large programs that are running, we decide in advance how many nights each semester or each year are going to be allocated to those large programs, which decreases the pool of nights for PIs. However, there's still quite a high number of nights. It's probably like half and half, depending on the semester and what we are working on. But there's still a fair chunk of nights for PI programs. And what happens is that if the pressure is too high, if there's too many proposals, some of them won't be accepted, they won't be put on the telescope, but there's always the possibility of resubmitting the proposal for a further semester later on to try to boost the ranking and the priority of that program.
I may add one more thing, since Nadine is a bit too modest to say this. All of the instrument scientists at CFHT are absolutely wonderful, and they do an amazing job of making sure that even lower priority targets get observed. If the weather conditions are a little too bad for, say, high priority targets, they do a really wonderful job.
Yeah, there's one thing I didn't mention. We offer kind of freebies. If you have objects, targets, or projects that can use bad sky conditions, an image quality or seeing of 1.2 arc seconds or worse than that, or if you can tolerate clouds with espidons, you can submit a snapshot proposal. And unless there's something really wrong with the snapshot proposal, it will be accepted. And I said that it comes as a freebie because we don't charge the agencies for those snapshots. They really come for free because it's a way to take advantage of really bad weather conditions. And for Mauna Kea, bad is 1.2 arc seconds. But we're very happy to conduct science under bad sky conditions if people have ideas. So if you want to try something and you don't need exquisite seeing or great sky, submit a snapshot program, please, on any of the instruments, and we'll see if we can perform them.
Thank you very much for explaining that. So we have another question from AJ asking, is there any priority given to proposals submitted by graduate students / early career researchers?
I don't know if or how the tax take into account that information, because the information is in the proposal. If the proposal is attached to a student, a PhD project, you can mention that. However, we also have access to that information. And when we know that a student really needs data because they really want to finish their thesis, we try to make it happen. So we understand under what kind of pressure graduate students are, or even early career researchers, and we try our best to balance everything out to make PIs as happy as possible.
Great, thank you very much for that. Are there any other questions? I should ask again and wait a moment this time.
I could also mention, because I didn't, that we do have from time to time interns. We don't have a formal program. So we don't have, we don't have announcements where we say, this is the season for internships, please apply. We don't have anything formal like that, but if somebody is interested, send us an email. We will try to fit you, depending on your interests and skills, we'll try to fit you with one of our astronomers on a small project that you can carry on.
Yes, thank you for mentioning that. I in fact, was an intern at Cfht, and it's a wonderful experience. So we do have another question in the chat from Matthew Buchan. I was wondering what we have to do to work on the instrumentation / engineering side at Cfht.
So we have a great team of technicians and engineers that do optics, mechanical design, mechanical fabrication, software, basically all the areas of engineering. So if you have a degree which is relevant for the type of skills that we are looking for, you can apply. And of course, if somebody has experience at an observatory working for a telescope, even if it's in the space industry, that adds a little bit more to your set of skill, and that becomes very interesting.
Great, thank you for that. Okay, it looks like we're all set with the questions. So once again, I will thank you, Nadine, very much for giving this wonderful presentation. This is a perfect initiation to the CaTS series. So thank you once again. I would like to give everybody a quick reminder that we are going to be having our next seminar on April 28th. It's going to be given by Dr. Steve Mayers at the James Clerk Maxwell Telescope. And if you want more information on that, of course, we'll send out a Casca blaster, but I also encourage you strongly to follow us on social media, Instagram, Facebook, or Twitter, under the handle Casca GSC, that's one word. And we put out a lot of updates on that, and of course, with our other programs of the Casca GSC. So once again, thank you so much, Nadine, and thank you very much, everybody, for coming.
Thanks, Nadine.
Thank you. Have a good day.
Take care.